Hi everybody, so this is not going to take very long. We only have a couple of slides to run through, and then you're going to work on a Doppler shift worksheet that we will go over tomorrow when I'm back, and then we'll also do the spectrometer or spectroscope lab as well tomorrow. So here we go. So get your notes out. Let's finish these up. Okay, so we've been talking about the spectrum. You did your spectral lab or spectra gizmo yesterday, and it kind of showed how we can identify different elements in stars based off what spectra we are looking at and what spectras are missing. So for example, when you see a light bulb or other source of continuous radiation, all the colors are present. When the continuous spectrum is seen through a thinner glass cloud, the cloud's atoms produce absorption lines in the continuous spectrum. When excited cloud is seen without the continuous source behind it, its atoms produce emission lines. We can learn these types of atoms are in the gas cloud and their patterns of absorption or emission lines. So every element is going to look just like that continuous spectrum with the dark lines or the bright line spectrum, depending on which one you're looking at. Depending on what is missing is going to give a big indicator of what elements are within that glass or gas cloud. So when we're trying to figure out what the composition of stars are, that's a lot of what we're looking at, is what lines are missing to then tell us what type of elements have to be there based off what is being absorbed and reflected. Not ready for the video quite yet. Okay, the Doppler effect. So this is basically what your whole worksheet's about. So when a source of light is approaching or receding from an observer, the light waves are crowded closer or spread out. So it's just like, for example, when you're driving your car and you hear an ambulance. When it's really far away from you, it is really quiet. So you can slightly hear it. So then you start looking to see where the fire truck ambulance is coming from. Then once it comes past you, it gets really, really loud because those sound waves are getting scrunched closer and closer together. Then as the ambulance or fire truck moves away from you, it starts getting quieter because those sound waves have to spread out further and get to you a lot longer distance. So same idea here when it does come to light. Things are going to appear brighter when they're coming towards us, dimmer when they're farther away. So this video does a nice job explaining what the Doppler effect is.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change colour depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so especially that red and blue shift. Again, the longer the wavelength, the more red something's going to appear. The shorter the wavelength, the more blue something is going to appear. And not necessarily in color per se, but for what we call it is red or blue. And that just means the longer wavelength or shorter wavelength. In astronomy right now, we're viewing everything as a red shift because everything is moving away from us. Occasionally we will notice something that might appear moving closer. So if we're looking at like an asteroid or something that's reflecting sunlight, then we may view it as a blue shift because it's coming towards us. And again, red shift just means those wavelengths are getting longer, more distance between us. Blue shift, those wavelengths are coming closer, and meaning the wavelengths are a lot shorter. Okay, so here is kind of an example of those different shifts that we see depending on where the observer is based off the movement that is occurring. So the first one is showing the stationary movement, so that's letter A there. So if something was stationary, we really wouldn't view a huge mass change of movement. But if we're looking at B, depending on which observer you're dealing with, they're going to view it at a different wavelength because of the distance it has to travel. So if you're looking at the observer A, those wavelengths are going to be a lot shorter, and so you're going to see a more blue shift. If you're looking at observer C at the very top, that's going to be considered a red shift because as wavelength spreads out, so it's going to take longer for those wavelengths to get to you. Okay, so I'll do the demo tomorrow. It's nothing super fancy, but for the rest of the period, you're going to work on the Doppler shift activity. You're going to have to ask the sub if they're going to let you work with other people or not. But the rest of the time, finish that up. Come with questions tomorrow, and we'll review, and then we'll also do our lab. Have a great rest of your day. I will see you tomorrow.